Hello friends, welcome to another lecture, that is lecture number 5 of Laplace Transformation, and please watch the previous lecture, link is in the description box. Please like, share and subscribe the channel and also hit the bell icon, and you can follow me on Insta ozalekajit123, that's my Insta ID. So if you have any doubts, any question that you cannot solve, you can send me there. Okay, so now let's start the video. So here is the first question. We need to find the Laplace transformation of this. So we know this that if Laplace transformation of a function f of t is suppose capital F of s, then Laplace transformation of t to the power n into f of t is given by minus 1 to the power n nth order derivative with respect to s of capital F of s. So we're going to apply this. So now let me show you how to do that. So here we are to find Laplace transformation of t to the power 3 e to the power minus 3t. Okay, so first here we are going to consider this e to the power minus 3t as f of t, right? F of t. So Laplace transformation of f of t, in this case e to the power minus 3t, is that's going to be 1 by s plus 3, if you remember the formula. So this is our f of s, capital F of s, right? Then according to this theorem, so Laplace transformation of Laplace transformation of t to the power 3 dot e to the power minus 3t, that should be minus 1 to the power 3, here n is 3, and third order derivative with respect to s of f of s, here f of s is 1 by s plus 3, right? So 1 by s plus 3. So now, so here you see this is third order derivative. First let us differentiate with respect to s 1 by s plus 3. First let us differentiate it once. So if you differentiate it, then you have to assume this one as s plus 3 whole to the power minus 1. You can assume that way. In that case, then its derivative will be minus s plus 3 whole to the power minus 2. So you can simply write minus 1 by s plus 3 to the square, whole square. You can write that. So let me scroll down the page. Then you will get minus 1 cube is minus 1 simply, and here you will get now after differentiate once you will get second order derivative. So here minus 1 plus 3 whole square, that's what we will get. Now again we are going to differentiate it. So if you differentiate here you see now this minus it's become positive, right? So now differentiate again. So we can, now you say this 2 becomes positive, so we can ignore the minus sign here. Again differentiate 1 by s plus 3 whole square, right? 1 by s plus 3 whole square, it can be considered as s plus 3 whole to the power minus 2. In that case you will get minus 2, right? You will get minus 2 s plus 3 whole to the power minus 3. So that is nothing but minus 2 by s plus 3 whole cube. You can write that way. So d by ds you will get minus 2 by s plus 3 whole cube. Now again we need to differentiate it, right? If you differentiate it again, then what you will get? So now let me scroll down the page. Okay. So this minus 2 can be written outside. So if you differentiate it, what you will get? You can assume s plus 3 whole to the power minus 3. You can assume that. So we can write 1 by s plus 3 whole cube as this, right? So now its derivative will be, So minus 3 minus 2, that's going to be minus 6, right? Sorry, plus 6. Then and you will get s plus 3 whole to the power minus 4. So that can be written as 6 by s plus 3, 6 by s plus 3 whole to the power 4, right? So our final answer is 6 by s plus 3 whole to the power 4. So that's how we can solve. So this is the Laplace transformation of this function. So hope you have understood. Now let's move on to another question. Now our next question is we need to find the Laplace transformation of t dot cos hyperbolic at. So how to find the Laplace transformation of this? Laplace transformation of t dot cos hyperbolic at. So now you see here, this cos hyperbolic at should be considered as f of t now, right? So again we are going to apply the same thing. If Laplace transformation of f of t is capital F of s, then Laplace transformation of t dot f of t is given by minus 1 to the power n on nth order derivative. So suppose you have not t only, t to the power n, then nth order derivative with respect to s of f of s. As we have t to the power 1 here in this case, so it's going to be simply minus d by ds of f of s, right? As n is equal to 1 in this case, because we have t to the power 1, if you see here, right? So now Laplace transformation f of t, our f of t is in this case cos hyperbolic at. So Laplace transformation of cos hyperbolic at, you have already got this one. In previous lectures we have already discussed the formulas, right? In earlier lectures, lecture 1 and 2, I think. So what's all the lectures? So that should be s by s square minus a square, right? So this is our capital F of s. So now according to this theorem, Laplace transformation of t dot cos hyperbolic at, we should get minus 1 to the power 1, that means minus 1, and first order derivative of f of s. So our f of s is here s by s square minus a square. That's what we get. So now let's come to derivative. So here you see we are going to apply this derivative of u by v. So it's given by v derivative of u minus u derivative of v. That means denominator derivative of numerator minus numerator derivative of denominator by denominator square. So that's what we're going to apply here, right? So if you apply that, what you will get? So here this s should be considered as u and this denominator should be considered as v. So in that case, let me scroll down the page. So in that case, s square minus a square, derivative of s, that's going to be 1, right? Minus s, and derivative of v is here, this one, s square minus a square. If you differentiate it, you will get twice s, and derivative of a square will be 0 definitely, by denominator square s square minus a square, that's going to be whole square, right? So hope you have got it. So what we have done here, just s square minus a square derivative of, let me write here, s minus, so this is our v, this is our u, right? So derivative of s means u dash, then u, that means s into derivative of v dash, that is derivative of s square minus a square. So hope you have understood this, s square minus a square. Right? And by s square plus, sorry, s square minus a square whole square. So this quotient formula is applied here. Okay, so hope you have understood. The S is simple derivation, and so s square minus a square minus twice s square by s square minus a square. Sorry, I have forgot this one. This minus sign should be written here. Okay, sorry. So, and here also we have minus this, okay, whole square. Then if you simplify this, you will get 2 minus 2s square, s square minus 2s square, that's going to be minus s square. And if you multiply this minus, then you will get plus s square, and this is going to be also plus on multiplication of this minus, and then you will get s square plus a square by s square minus a square whole square. That is our result. So hope you have understood this. Now let's move on to next question. Now here you see we are going to find a Laplace transformation of this. So here again we are going to apply this. If Laplace transformation of f of t is capital F of s, then Laplace transformation of t to the power n dot f of t is given by minus 1 to the power n and nth order derivative with respect to s of f of s. So that's what we're going to apply here. So now here you see, so we need to find the Laplace transformation of t square dot sine t. So what will be the result? So again here this f of t should be considered as sine t, right? So Laplace transformation of sine t, if you remember, Laplace transformation of sine a t is a by s square plus a square, but here a is 1, so 1 by sine square plus 1 square, that is 1. So this is our capital F of s in this case. So now according to this theorem, then Laplace transformation of t square, sorry, instead of n we have square now, sine t, that's going to be equal to minus 1 square, that's going to be plus 1, so we can ignore it. So second order derivative of f of s, here f of s is 1 by s square plus 1, right? That's what we will get. Now you see we have second order derivative, means we need to differentiate it twice, right? So if you differentiate it once with respect to s, so this 1 by s square plus 1 can be written as s square plus 1 whole to the power minus 1. So you can consider as this whole thing as s, then s to the power minus 1. If you differentiate it with respect to s, then you should get minus s whole to the power minus 2. But here you see, instead of s we have now s square plus 1 whole to, right? So it is function of function. Again we need to differentiate this expression within the bracket. So then what you will get, so if you differentiate it once, then you should get minus 1 into s square plus 1 whole to the power minus 2 into, as it is not an s, if you had s, then you're supposed to get minus s to the power minus 2. Instead of s we have s square plus 1. If you differentiate it as s square plus 1, then what you will get again, so let me clean this part. Okay, then s square plus 1 derivative, its derivative gives you twice s, right? So that's why it gives you minus 2s s square plus 1 whole square. That's what you will get. So here you see, so let me scroll down the page. So we have differentiated once, so this minus 2 can be written outside, so minus 2. So now only first order derivative left here. So s by s square plus 1 whole square minus 2, we have written this minus 2, this minus 2 outside, so we had minus 2 here, no? So this minus 2 written outside the derivative. Okay, so now here we are going to apply this rule. U by v, derivative of u by v is given by v derivative of u minus u derivative of v by v square, right? Consider this as u and this one as v, denominator as v, numerator as u. So if you consider that way, then what will be its derivative? If you differentiate it again, then what you will get, let me write here, minus 2 denominator, that is s square plus 1 whole square, and derivative of the numerator dds of s, that's going to be 1. So let me write directly 1, okay, into 1. So minus then s, derivative of the denominator, derivative of this s square plus 1 whole square. If you differentiate this, derivative of s square plus 1 whole square, so considering this one as first considering this one as s square, if you differentiate s square, then you should get twice s, right? So in that case you should get s square plus 1, 2 into s square plus 1. So but here it is not only s, so it is function of function s square plus 1. Again you need to differentiate this term within the bracket. If you do that, then you will get again twice s, right? So that's why let me write here, instead of writing this, so let me write the result here. You will get 2 into s square plus 1 into twice s. That's what you will get. So s square plus 1 whole square, right? So now then denominator is square v square. So here denominator was s plus 1, s square plus 1 whole square. So again we need to square this. That's what we will get. So now what you can do here, you can say you can take this common, right? S square plus 1 common. So let us take that common. Then minus 2 into s square plus 1 is taken common. Then within bracket you will get s square plus 1 minus twice s into twice s. That's going to be 4s square, right? So denominator is s square plus 1 whole to the power 4. Now here you see, if you cancel this s square plus 1 whole to the power 4 by s square plus 1, then you should get s square plus 1 whole cube, right? So then our result becomes minus 2 into, so here s square minus 4s square, that's going to be minus 3 square, right? 1 minus 3 s square, not 3 square, minus 3 s square by s square plus 1 whole cube, right? So if you multiply this minus here, then what you will get, minus 3s square plus 1, not plus 1, minus 1, that's going to be minus 1, and s square plus 1 whole cube. So this is your answer. That's how we can find. So this is the Laplace transformation of so let me minimize it. So this is the Laplace transformation of this Laplace transformation of t square dot sine t is this one. This is the required Laplace transformation. So hope you have understood this. So now let's move on to next question. Now we are to find the Laplace transformation of t into sine square 3t. So again we are going to apply the same formula. If Laplace transformation of f of t is capital F of s, then Laplace transformation of t to the power n dot f of t is given by minus 1 to the power n nth order derivative with respect to s of f of s. That's what we're going to apply here. So here Laplace transformation of, let me write the solution, t dot sine square 3t, that's what we need to find. So our f of t should be considered as sine square 3t. So Laplace transformation of sine square 3t. So sine square 3t. So here we are going to apply this, that sine square theta, we know sine square theta is 1 minus cos twice theta by 2, right? So here theta is nothing but 3t. So here 2 theta will be 60, right? So if you apply that, then you can write this one as Laplace transformation of 1 minus cos 6t by 2. So, or you can write this way, you can write the half outside, right? 1 by 2 Laplace transformation 1 minus cos 6t. So that's going to be half into Laplace transformation of 1 minus Laplace transformation of cos 6t, right? That's what we will get. And Laplace transformation of 1 is nothing but 1 by s, and Laplace transformation of cos 80. Laplace transformation of cos 80 is s by s square plus a square, but here a is nothing but 6. So we will get s by s square plus 36, right? 6 square is 36. That's what we will get. So for us, this is our capital F of s. Okay, so now we're going to apply this theorem. So let me scroll down. So according to that, you should get Laplace transformation of t dot sine square 3t should be equal to, there is only t, so that's going to be minus 1 to the power 1, that is minus 1. So simply minus first order derivative, power on t is 1, so that's why first order derivative of f of s. Here f of s is half 1 by s minus s by s square plus 36. That's what we will get. So now again we need to differentiate, and what you will get. So let me scroll down. So from here, this half is constant, so it can be written outside. Then derivative of 1 by s. So derivative of 1 by s, this one will be simply minus 1 by s square, right? Because ddx of 1 by x is minus 1 by x square. We know that, right? So you got it. So now derivative of this, how to find the derivative of this? Derivative of s by s square plus 36. Again we are going to apply the quotient theorem, that is u by v, derivative of u by v. That denominator s square plus 36, derivative of numerator is s, right? The numerator is s, derivative of s should be 1, and minus s into derivative of s square plus 36, sorry, derivative of s square plus 36. So if you find the derivative of s square plus 36, derivative of s square is twice s, and derivative of 36 will be 0, so we will get s into twice s here, by denominator square is s square plus 36 whole square, right? That's what we will get. So let me write it clearly, twice s. So hope you have understood this. Then what we will get, let us simplify. S square plus 36 minus s into twice s, that's going to be twice s square by s square plus 36, right? So then twice s square minus twice s square, that's going to be 36 minus s square, we will get s square plus 36, right? So that is what we will get. So if you take minus common, then this numerator becomes this will become s square minus 36, right? So then this minus and this minus makes it plus, so we will get s square minus 36 by s square plus 36 whole square. So here we need to write denominator square, right? So this is what we will get after find the differentiation, after differentiating this f of s, right? That's what we will get. Now so let us multiply this minus with the terms within the bracket. Then what you will get, half 1 by s square, and this positive sign will be again negative s square minus 36 by s square plus 36 whole square. So this is our final result. So hope you have understood. That's how we can find a Laplace transformation of this t into s square 3t. So now let's move on to next. Now we are to find the Laplace transformation of this. So here t square e to the power minus 2t cos t. So solution, Laplace transformation of t square dot e to the power minus 2t cos t. We need to find the Laplace transformation of this. So here our f of t should be considered this one. So again we are going to apply this. If Laplace transformation of f of t is capital F of s, then Laplace transformation of t to the power n dot f of t, that's going to be minus 1 to the power n nth order derivative with respect to s of f of s. That's what we are going to apply. So before that we are going to find considering this part as f of t, Laplace transformation of f of t, that is e to the power minus 2t cos t, cos t. So here one more thing, again you see here we are going to apply this, in this case Laplace transformation of e to the power at f of t is equal to, if Laplace transformation of f of t is capital F of s, then it should be equal to f of s minus a, right? F of s minus a, when you have e to the power at multiplied with f of t, right? To apply this formula, you should consider this cos t as f of t for the time being. So before that, so let us find Laplace transformation of this cos t. So Laplace transformation of cos t, cos t, that's going to be, what is the Laplace transformation of cos t or cos at, right? So that is s by s square plus a square. A is 1 here, so it's going to be 1 square is 1 simply. So this is our f of s, right? So f of s. So then according to this formula, so if this is f of s, then Laplace transformation of e to the power minus 2t cos t, that should be s minus a is here minus 2, so s minus minus 2, that's going to be s plus 2, right? S plus 2 by, again s square will be s plus 2 whole square plus 1, that's what we will get. So applying this formula here, understood? So hope you have got it. So now we are going to consider this one as f of s, right? Now let us consider this result is as f of capital F of s. To find out the Laplace transformation of t square dot this, so this part is considered as f of t now, to apply this theorem. So hope you have understood this. So in that case, Laplace transformation of t square dot e to the power minus 2t cos t, that's going to be minus 1 to the power 2, that's going to be simply plus 1, so ignore it. So second order derivative of f of s is what we have got, s plus 2 by s plus 2 whole square plus 1, that's what we have got, right? Now let us solve this, right? Now let us solve this. Let me scroll down the page. So second order derivative means we need to find, we have to differentiate this twice. If you differentiate it for with respect to s once, then what you will get, s plus 2 by s plus 2 whole square plus 1. So here again we are going to consider this is as u and this one as v. Then applying this this quotient rule, that is u by v rule, derivative of u by v is v derivative of u minus u derivative of v by v square. If you apply that, then what you will get, denominator, that is s plus 2 whole square, s plus 2 whole square plus 1, that is into derivative of s plus 2, derivative of s plus 2 will be 1, then minus s plus 2 derivative of the denominator, derivative of this, derivative of this will be twice s plus 2, derivative of 1 is 0, yes, and derivative of s plus 2 whole square will be twice s plus 2. So that's then denominator is square, s plus 2 whole square plus 1 again whole square. That's what we will get. Now let us simplify this. If you simplify this, let me do here, what you will get. So s plus 2 whole square, it gives s square plus 4s plus 4, and plus 1 we have here, we have plus 1, so directly we can write, instead of 4 we can write plus 5. Okay, minus, then again s plus 2 into s plus 2, then we have a 2 here. If you see this, then what you will get after multiplication, twice s square and minus 8s, then minus 8. Okay, that's what we will get by denominator square. So if you again find this value, then what we will get, s square plus 4s plus 4 plus 1, that's going to be again 5, right? Here we have applied a plus b whole square, and this is 1. Okay, so now what we can do, let us simplify this first. So if you simplify this, what you will get, minus 2s square, that's going to be minus s square, s square minus 2s square, then 4s minus 8s, that's going to be minus 4s, and 5 minus 8, that's going to be minus 3. That's what we will get, right? So taking the minus common, so this negative sign inside the bracket will be positive, then s square plus 4s plus 5 whole square, that's what we will get. So after differentiating one, we get this, right? So let us write now, let me clean this part. So what we have got now, first order derivative left only. Let me write the minus sign outside the derivative. So here we need to differentiate it now, s square plus 4s plus 3 by s square plus 4s plus 5 whole square. We need to differentiate this. So hope you have understood the derivative differentiation. You know differentiation very well, I hope so. Okay, so now what we're going to do, again we are going to apply this u by v, derivative of u by v rule. Okay, so now let me clean this. Okay, so what we're going to do here, again we are going to apply this u by v rule, derivative of u by v, that v derivative of u minus u derivative of v by v square. Let us apply that again, considering the numerator as u, denominator as v. So if you do so, then what you will get, so minus denominator, here the denominator is s square plus 4s plus 5 whole square, derivative of the numerator, derivative of numerator, this is the numerator, s square plus 4s plus 3. If you differentiate it, then what you will get, twice s, right? And derivative of 4s is just 4, that's what you will get, right? Then minus the numerator is s square plus 4s plus 3, right? And derivative of the denominator, derivative of this, if you differentiate it considering s square, then you should get twice s into s square plus 4s plus 5, and then again you have to differentiate the terms within the bracket, then you will get twice s plus 4. That's what you will get. So let me write it cleanly, twice s plus 4, right? That's what you will get. Then again denominator square means s square plus 4s plus 5, and whole square, again whole square, that's 4, right, to the power 4. That's what we will get. So hope you have understood this. Now what we are going to do, okay, so again we can take common here, this and this should be taken common. If you take common and cancel with this, then what you will get, then you will get, let me write, so, or you can consider that both the numerator and denominator is divided by s square plus 4s plus 5. this one also divided, this one also divided by s square plus 4s plus 5, and here also it is also divided by s square plus 4s plus 5. If you assume that way, then what you will get? So our result will be, so let me clean this, then our result will be here we have a square, so only one term left, s square plus 4s plus 5 into 2s plus 4, and here we have s square minus plus 4s plus 3, and this is gone, 2 into 2s plus 4, and the denominator, instead of power 4 we will have power cube, s square plus 4s plus 5 whole to the power 3. That's what we will get after doing so. So now what we're going to do here, now we will multiply and simplify. That's it, that's all what we can do here. So let me scroll down the page. Minus s square plus 4s plus 5 whole cube. Now let's multiply these two. So what you will get? So if you multiply these two, then you should get so let me do here, twice s cube, then plus 4s square, then plus 8s square, then 8s, then you will get 10s plus 20. That's what you will get, right? So here you see 10s plus 8s, then what you will get? 2s cube plus 4s square 8s square 4s square 8s square, so that's gonna be 12s square, right? So 12s square plus 18s, then plus 20. That's what we will get, right? So hope you have got it. So now let's multiply this. So what you will get? If you multiply this, okay, let me check. So if I have done any mistakes, sorry, I have made a mistake here. This 4s and 4, that's gonna be 16s. It should be 16s plus 10s, that should be 26s. Okay, so let me clean this. So we should have here 26x, 26s, right? So that is what we will get. Now let us multiply this. If you do so, then what you will get? And 2 to the 4 into s, then s square, that's going to be 4s cube, then again s square with 2 into 4, that's going to be 8 into s square, this is 8s square, then 8 is square, sorry, so here we should get 8s square, then what we will get, 4 into 4s, that's going to be plus 16s square, 4s into 4s, 16s square, then 4 into 4s into 8, that's going to be 32s, right? 32s, right? Then by 3, now if you 3 multiply here, 2 into 2 4s, then 12s, then 8 into 3 24. That's what we will get. So now if you add those, then what you will get? So we have minus sign here, so sign will be changed, minus 4s cube, then minus, so 8s square, then 16s square, that's going to be 24s square, then this positive signs becomes negative because of this minus sign, Okay, so be careful with that. Then 32s and 12s, that's going to be 44s minus 44s, then minus 24. That's what we will get. So hope you have got it. So now let me clean this part. Okay, now do addition, subtraction, whatever you can do here, then you will get the answer, right? Okay, let me scroll down the page. Then here you see minus 2s cube minus 4s cube, that's gonna give you minus 2s cube. So multiplication of this minus sign, then you will get plus 2s cube, right? Then again minus 24s square plus 12s square, that's going to be minus 12s square. Multiplication of this minus gives you plus 12s square, right? Then minus 44 plus 26s, that's going to give you 18s minus 18s. Because of multiplication of this minus, you should get plus 18s, right? So sorry, plus 18s. Then again minus 24 plus 20, that's gonna give you minus 4. And because of this minus sign, here you will get plus 4, right? So now let us take 2 common. So here s square plus 4s plus 5. So this should be cube, okay, whole cube. This expression here, you see denominator should be whole cube. It is whole cube, right? Now let us take 2 common. Okay, so if you take 2 common, then you will get 2 s cube plus 6s square plus 9s plus 2 by s square plus 4s plus 5 whole cube. So this is the Laplace transformation. This is the Laplace transformation of this function t square e to the power minus 2t cos t. Okay, so this is the Laplace transformation of t square e to the power minus 2t cos t, right? So this is the Laplace transformation. So hope you have understood this. Now let's find the Laplace transformation of this expression, this integral function. So here Laplace transformation of integration 0 to t e to the power minus 2t dot t sine cube t dt. So we need to find the Laplace transformation of this function. Now here you see, so what we're going to do here in this case, we know that if Laplace transformation of f of t is f of s, then Laplace transformation of integration 0 to t of f of t dt is given by 1 by s f of s, right? 1 by s f of s. So here, to apply this theorem, we are going to consider this part as f of t. So then we need to find first Laplace transformation of t dot sine cube t dt, right? We are going to find this. So to find this, again you see here we are going to apply this, that if Laplace transformation of f of t is f of s, then Laplace transformation of t to the power n dot f of t is equal to minus 1 to the power n nth order derivative with respect to s of capital F of s. So we are going to apply this. So in this case also, this f of t that we have taken here in this theorem, that should be considered as this sine cube t dt. So first of all, before we find Laplace transformation of t dot sine cube t dt and Laplace transformation of integral of e to the power minus 2t t sine cube t dt, we need to find the Laplace transformation of sine cube sine cube t, right? So here dt should not be written. Okay, so now what will be the Laplace transformation of sine cube t? So sine cube 2 is a sine cube t. This can be written as Laplace transformation of sine cube t is nothing but here we're going to apply this sine 3t is equal to 3 sine t minus 4 sine cube t minus 4 sine cube t. So if you simplify this, then you will get sine cube t is equal to 3 sine t minus sine 3t by 4. That's what we will get. So we will get 3 sine t minus sine 3t by 4. That's what we will get. So hope you have understood this. So now let me clean this. Okay, so what we can do here, let me scroll down the page. So this can be written as 1 by 4 Laplace 3 into Laplace transformation of sine t minus Laplace transformation of sine 3t, right? We can write this way. So now Laplace transformation of sine t, that's going to be 1 by sine square plus 1, and that of sine 3t will be 3 by sine square plus 3 square, that is 9, right? You're going to get this. So 3 can be taken common, then you will get 3 by 4 and 1 by s square plus 1 minus 1 by s square plus 9, right? So now, so you can see for this, if you consider this as f of t, then you can consider this one as f of s. If you consider that, then apply this formula here now to find t dot sine cube t. So Laplace transformation of t dot sine cube t, so 1 to the power minus 1, that's going to be simply minus 1. So you can write minus first order derivative simply. Our f of s, that means Laplace transformation of sine cube t, we have got 3 by 4 1 by s square plus 1 minus 1 by s square plus 9, right? So we have got this. Now you see this 3 by 4 can be written outside and with the minus sign, so we can find derivative of 1 by s square plus 1 minus derivative of 1 by s square plus 9. So let us find the derivatives. Then what you will get? Minus 3 by 4. If you consider this one as s square plus 1 whole to the power minus 1, then you will get its derivative. Its derivative will be minus s square plus 1, and again if you differentiate it, minus 2. If you again differentiate it, you will get twice s. That means you will get twice s minus twice s by s square plus 1 whole square. That's what you will get if you differentiate this, right? If you differentiate this, you're gonna have this result. So now let me clean this. So what we have got, let me put that one directly. Okay, so we will get minus twice s by s square plus 1 whole square. Similarly, if you differentiate this, then you should get minus twice s by s square plus 9 whole square. That's what you will get, right? Then if you multiply this minus with this, then what you will get? This negative sign will be positive, right? Then you will get positive. So hope you have understood this. So now, so here you see, if you consider this one as Laplace transformation of f of t, to apply this theorem, to apply this first theorem in this case to find out this integral, okay, if you consider t dot sine cube t dt as sine cube t as f of t, then this is the Laplace transformation of f of t, that is capital F of s. You can consider this one as capital F of s. In that case, Laplace transformation of integration 0 to t e to the power e to the power minus 2t, then one more thing, before we find the integration, again we need to find this e to the power Laplace transformation of e to the power minus 2t t dot sine cube t. So because you see, now we are going to apply this theorem that Laplace transformation of e to the power at f of t is equal to 1 by it is f of s minus a if Laplace transformation of f of t is capital F of s, right? If Laplace transformation of f of t is capital F of s, then Laplace transformation e to the power at dot f of t is capital F of s minus a. So if you apply that, then here you see, you should consider this one as f of s. You should consider this one as capital F of s. Now, so let me clean this. Then what you will get? Then you should get 3 by 4 2s. Instead of s, we will get s minus minus 2. That's going to be s plus 2, right? S plus 2. So here a is minus 2, right? E to the power a is minus 2 here by s plus 2 whole square plus 1, right? Again whole square minus 2 into again s plus 2 by s plus 2 whole square plus 9 again whole square. So we will get this. Now we are going to find the integral. So Laplace transformation of integration 0 to t e to the power minus 2t t dot sine cube t dt. So here you see, we are going to consider this one as this whole thing as f of t, right? So if that is f of t, then Laplace transformation, this is Laplace transformation of f of t, that is, this is capital F of s. We can assume that way. So hope you have understood. Then we should get 1 by s capital F of s. Here capital F of s is 3 by 4 2 into s plus 2 divided by s plus 2 whole square plus 1, then again whole square minus 2 s plus 2 by s plus 2 whole square plus 9 again whole square, right? So if you simplify this, then what you will get? 3 by 4 s, you can take 2s plus 2 common. You can take 2s plus 2 common, right? If you take 2s plus 2 common, then what you will get? 1 by s plus 2 whole square plus 1, then whole square minus 1 by s plus 2 whole square plus 9 again whole square, bracket closed. So here you see this 2 cancels 4, you will get 2 here. So our final result is 3 into s plus 2 by 2 and 1 by s plus 1, not 1, s plus 2 whole square plus 1, then again whole square minus 1 by s plus 2 whole square plus 9, then again whole square, right? So that's going to be our result. So this is nothing but the Laplace transformation of integration 0 to t e to the power minus 2t t sine cube t dt, right? So that's what we need to find. Okay, so this is our last question. that we are going to solve today. So here this function f of t is continuous except this point at t is equal to a. At this point only this is discontinuous. Okay, it is discontinuous at t is equal to a at this point, right? You can see clearly from the figure. Okay, so then we have to prove this. Okay, so now here you see, by definition of Laplace transformation, that Laplace transformation of derivative of f of t, that is equal to 0 to infinity e to the power minus st transform derivative of f of t dt, right? This is by definition. This is by definition. Right? Now you see, here we are going to split this from 0 to a, then a to infinity, in that way. So if you do that, then you can write 0 to a e to the power minus st derivative of f of t dt, then plus 0 to, sorry, not 0 to, a to infinity e to the power minus st f dash of t dt. That's how we can write. Now let me scroll down the page. Here you see, if you integrate this, then applying this integration u v dx, that's equal to u integration of v dx minus integration derivative of u integration v dx whole dx. So if you apply this product rule of integration, then what you will get, sorry, so then you should get, let me clean this first, then you will get e to the power minus st integration of f of t, integration of f dash of t, that's going to be f of t, right? So we have limits here, 0 to infinity, sorry, 0 to a, let's put here 0 to a, then minus integration 0 to a, so then derivative of this e to the power, this is minus s e to the power minus st, right? Then again integration of integration of f dash of t, so that's going to be again f of t, right? Its integration is f of t, then dt. That's what we will get. Again same thing is applied here also. So if you do that, then plus e to the power minus st f of t, right? Only limits are different here, a to infinity, then minus 0 to a minus s e to the power minus st. Results are same, only limits different. So here 0 to infinity, sorry, f of t dt. That's what we will get. So hope you have understood this. Now if you put the values here, you can see, if you put the values limits a and 0, okay, upper limit and lower limit, then what you will get? So at a you will get e to the power minus sa. If you put here a, then from the diagram what you can see, that should be while you are going 0 to a, it should be f of a minus 0 at a, right? It should be f of a minus 0, okay, at a. Then when you will put 0, then you should get this part will be, sorry, not this part, so this e to the power minus st will be 1, and f of 0 we will get f of 0, right? Then you can recombine these two, and here you see this minus it will be plus, and this minus into this minus, that will be plus again. So if you recombine these two, then you will get plus 0 to here we have 0 to a, sorry, it should be a to infinity, 0 to a and a to infinity, so directly you can write 0 to a, sorry, infinity, 0 to infinity, then s e to the power, so you can write the s outside, s e to the power minus st f of t dt. Again, so we have evaluated this. Now let us evaluate this. So again, if you put infinity here, then it's gonna be 0. If you put a here, then what you will get? You should get on putting a, you will get minus, as it is lower limit, minus, on putting infinity you will get 0, plus 0 on putting a, this lower limit, minus. So what you will get? Minus s a f of a. Okay, so while you go a to infinity, then here at a, the point is f of a should be f of a plus 0. It should be f of a plus 0 at a. So it should be f of a plus 0. Sorry. A plus 0. That's what we will get. So if you simplify this, what you will get? S into 0 to infinity e to the power minus st f of t dt minus f of 0, right? And from these two terms you can take this common. E to the power minus sa can be taken common. If you take e to the power minus sa common, then what you will get? If you take the negative sign common, then you will get f of a plus 0 minus f of a minus 0. That's what you will get. Now you see, by definition of Laplace transformation, this should be Laplace transformation of ft, right? F of t. So finally what we will get? S into Laplace transformation of f of t minus f of 0 e to the power minus s a f of a plus 0 minus f of a minus 0. That's what we will get. This is the required result, isn't it? This is equal to what? Laplace transformation of f dash of t. So Laplace transformation of f dash of t, right? So we have got Laplace transformation of f dash of t. So that's what we need to prove. So hope it is clear to you now. So that's what we had proof. This is the question, right? So if you like the video, if you have understood, please share with your friends and subscribe the channel. Thank you for